Good morning everyone. I'm honored to present to you a project in the field of water treatment titled the Semi-empirical model approach for specific energy consumption in reverse osmosis units. So this presentation is divided into different parts. We have historical background, basics of reverse osmosis process, system design, factor affecting the reverse osmosis performance, the specific energy consumption, and finally conclusion. So about historical background, reverse osmosis has come a long way for its theoretical foundation in the 18th and 19th centuries to its widespread application in the 21st century. The technology has revolutionized water treatment, providing a reliable method for producing clean water from various sources, including seawater, brackish water, and wastewater. As a global water challenge, process reverse osmosis is expected to play a critical role in ensuring access to safe and clean water for future generations. This figure gives an approximate representation of the salinity range to which the main desalination process can be generally applied economically. So the basics of reverse osmosis process. This is the first one. We must know what does mean osmosis. So osmosis is a natural process where water molecules move across a semi-permeable membrane from a region of low solute concentration to a region of high solute concentration. This movement continues until equilibrium is reached. Reverse osmosis, as the name suggests, is the reverse of natural osmosis process. It requires the application of external pressure to overcome the natural osmotic pressure. This pressure forces water molecule to move from a region of high solute concentration to a region of low solute concentration throughout a semi-permeable membrane. So about system design. So we have the figures in this parts illustrate the different system design. So in the first one we have the continuous process mode. The reverse osmosis system is divided into 6 types. An reverse osmosis system is usually designed for continuous operation, in which the operation condition of every membrane elements in the plants are constant with time. So the semi-batch mode is a modification of batch mode. In semi-batch mode of operation, the fed tank is provided with fed water during operation. The batch is determined with the fed tank full of concentrate. This allows a small tank to be used. Batch systems are usually designed with a constant fed pressure and decline in the permeate flow as the fed becomes more concentrated. In a single stage system, 2 or more models are arranged in parallel. Fed, product, and concentrate lines are connected to manifolds. Other aspects of the system are the same as in a single model system. Single stage systems are typically used when the system recovery is less than 15% in desalination, in seawater desalination. Systems with more than one stage are used to achieve higher system recoveries without exceeding the single element's recovery limits. Usually 2 stages will suffice of recovery up to 75%, and 3 must be used a higher recovery. Multi-stage system can also be designed with eternal concentrate recirculation for each stage using a separate recirculation pump. And finally, the concentrate of the second reverse osmosis is recycled back to the fed of the first reverse osmosis, because its quality is usually better than the system fed water, because the fed water of the second reverse osmosis is of high quality, and the second reverse osmosis can be designed for a higher flow and recovery than the first reverse osmosis. Here we have several parameters that influence the specific energy consumption in reverse osmosis unit. such as pressure, temperature, recovery rate, and finally the feed concentration. In the first figure, with increasing effective feed pressure, the permeate total dissolved solid will decrease while the permeate flow will increase. And the second, if the temperature increases and all other parameters are kept constant, the permeate flow and the salt passage will increase. And the recovery is the ratio of permeate flow to feed flow. In the case of increasing recovery, the permeate flow will decrease and stop if the salt of concentration reaches a value where the osmotic pressure of the concentrate is as high as the applied feed pressure, and the salt rejection will drop with increasing recovery. And finally, this figure shows the impact of the feed water salt concentration on the permeate flow and the salt rejection. So the goal of this study is to examine the performance of a semi-empirical model for calculation the specific energy consumption in reverse osmosis process. We have introduced a simulation tool for comparison. For this comparison, we explore the temperature range between 10 and 35 and also the recovery rate from 13% at 65% and the pump efficiency. From this figure, notably temperature sustainability impacts energy variation in specific energy consumption for semi-empirical model, a dynamic observed in both single-stage and two-stage units. Further, what is truly remarkable in this consistent superiority of the semi-empirical model over the simulated model across every curve depicted in this figure. This phenomenon holds for all scenarios encompassing both membrane types and stage within the study. It underscores the robustness and effectiveness of the semi-empirical model employed in this comprehensive analysis. In inclusion of an energy recovery device system has an impact on the semi-empirical model and its evolution within both single-stage and two-stage reverse osmosis units. In this instance, from figure, the simulation model surpassed the semi-empirical model across both membrane types and in both stages. Additionally, an observation is that with increasing temperature, the disparity between the semi-empirical model and simulated model becomes more pronounced, particularly at recovery rate equal 13%. Another observation to highlight is that within both single-stage and two-stage feeds, the semi-empirical model exhibits almost a linear progression for both membrane types. And finally, regarding the semi-empirical model and the presence of an energy recovery device, we codified a prototype with a recovery system to compare within the experimental measurements. However, in this case, the model has the same parameters as in the absence of energy recovery device, with the difference lying in the existence of this process. At present, we aim to extend the application of the semi-empirical model to various scenarios and conduct multiple trials with seawater to ensure the credibility of the presented values. The validation process involves subjecting the model to the real-world condition and a broad range of application therapy, confirming its robustness and reliability. And thank you for your attention.